Involved and had the good fortune to work for some the best companies in the audio and acoustics test and measurement world, starting with Brüel & Kjær, working with very nicely with my colleague Wim van Barneveld back in the US in the 1980s. Then I went on to Bose Corporation, worked with Listen Incorporated, a Brüel & Kjær spin-off, to help them get started. I've also had the good fortune of working with my former Brüel & Kjær colleagues, blocks that represent, let's say, very much an analog-only signal path. Those blocks that are either purely digital or a combination of analog and digital, and those blocks that are purely from a DSP standpoint. So I'll just go through this somewhat quickly, and we can just look at the different color schemes in here, because there's many of these. But as you'll see, there's a pretty wide mixture of what's going on in these different domains. Now, I'm making an assumption that might be completely false, that this world in here of TV and FM radio would be purely analog. I know in the US it's all 100% digital now, but for someone who has a smartphone that can also receive TV signals and also be an FM receiver, the FM still may be, the audio still may be coming in the analog world. You definitely have analog here, where you've got microphones, although this is changing quickly because the area of digital microphones. I'm just curious, how many here are aware of MEMS, micro electromechanical structures, and these digital mics? Okay, a couple of hands have gone up. So again, that's another area that is expanding that the instrument can handle, both on the input side to the instrument, and if the instrument's got a signal generator on the output side. Because there are people that will mistakenly take an amplifier out and plug it into the generator, and now you've got 20, 30, 40 volts going into something that the signals always want to come out of, but you're trying to shove something in there. So you don't want to be, blowing up your equipment. So these are important pieces of information to know. Low noise and distortion is absolutely critical. I mean, minus 100 dB or better. In the case of the AP, depending which model, it can vary between minus 106 and minus 118 dB. But oftentimes, products being measured, even the lower cost A to D converters on the market and D to A's can have this or even better performance. And high-end equipment could easily be 15 to 20 dB better than that. There's op amps on the market now, high-end op amps, that actually their noise characteristics are running into the noise floor of the high-end measurement equipment that's out there, with some of the different signals being used. Before I go through that, just real quick, just so you have a better understanding of what it is that you're looking at on the screen. This is the software interface to the APX analyzer series. So in this upper corner is what's called the sequencer. And the sequencer is where you choose a large number of tests or a small number of tests, depending how many tests that you want to do. And the measurements that now exist in the software, as you can see, there's a lot of stuff. You've got basic audio measurements that I talked about before, measurements that are meters, meaning just a single value is being presented, different types of sweeps, and I'll be demonstrating many of these, many different means of doing distortion measurements, measurements associated with crosstalk, perceptual measurements, which are being used in the primarily in the telecom industry, but I think these will start to be used more and more, in particular with streaming of audio over the internet and Wi-Fi networks, and using lossy compressions. I think these algorithms will be used more in the future. And then audio precision is now moving more into the acoustic testing world, and I'll demonstrate some of that. In this lower corner, there are monitors that run in real time, and the software itself was written to be working with a much higher resolution. We're having 1024 by 768. So to see a lot of these in detail, I just need to undock them. But you have running in real time, you have an oscilloscope, an FFT analyzer, the ability to look at some individual meters. Auxiliary control is just some simple 8-bit logic available, some specialized measurements for digital some information you can get about Bluetooth, etc., etc. So the idea behind the monitors is that you've got something running real time, so you can get some immediate feedback about your measurement setup. You know, if you have nothing plugged in and you look at your FFT and you're seeing giant 50 hertz and harmonics, that might be telling you've got some ground loop problems. This section in here is where you set up the physical connections to the analyzer, where you choose what sort of input or output that you have. So this particular analyzer has got numerous specialized modules. You know, every AP analyzer has X number of channels of analog, either it's a minimum of 2 analog output, 2 analog input channels, and then there could be a higher number of output and input channels. There's digital module for doing SPDIF, AES, EBU, Bluetooth, obviously for Bluetooth audio measurements, digital serial module for communicating at the chip level. So if you want to look at converters or look at signals just in, let's say, a DSP processor, you can do that. PDM is a new module that Audio Precision introduced, I think it was about 9 months ago. PDM stands for Pulse Density Modulation, and this is used primarily with these new MEMS, these digital MEMS microphones. And then ASIO is the driver used for many professional audio products. So if we're looking at ASIO sound cards or mixing consoles or other with this. And then for electronics as well as acoustics, especially for band-limited devices like telephones or headsets, you can sweep 2 tones, and then you can get the sum and difference products. So what I'm going to do in here is I'll get the FFT going, and let's see how this looks. And I'll just hit the start button, and we should be seeing these 2 tones. So we're going to start at 10K and work our way down to 2500 hertz, and there'll be 2 tones being played that are 100 hertz spacing. So let's see what we get here. Actually, what I'm going to do is just change my y-axis real quick. I don't think I'll have more than 100 dB, and I can put that in as 20. So let's see what we get here. So actually, I can just where's my zoom thingy? We'll just look at this, so we can just see the frequencies split a little bit more detail. Okay, so you saw those two pairs of frequencies. Now it looked like they were getting wider apart, but remember this is on a logarithmic scale. So when you are looking at intermodulation distortion, the typical analysis tool that is used is FFT, and looking at intermodulation distortion information, you should choose the x-axis, the frequency axis, to be linear, because that will show the intermodulation distortion products to be evenly spaced. And that's very useful because oftentimes, especially with electronics,